right? So we're going to be going over bond cleavage as well as bond formation, and then a little bit of mechanisms as well. So reaction mechanisms in general are just detailed description of how bonds are broken and formed. So that's why it's really important that we understand these. A concerted reaction is when multiple things occurring all at once in a one-step process. So that way it means we're just going to go straight from compound A to compound B. A stepwise reaction is when we have reactive intermediates and we are forming the product in a multi-step process. So A goes to some reactive intermediate, which is short-lived, and then that becomes B eventually. So it's important, again, concerted reaction and stepwise reaction, we are aware of these definitions, okay? So for bond cleavage, when we talk about bond cleavage, there's two types of bond cleavage. And that's going to be homolytic cleavage and heterolytic cleavage, okay? So first, symmetrical cleavage is called homolytic cleavage. So symmetrical meaning same, homo meaning same, homolytic, lytic meaning like lice something or cut it in half. So electrons are split between both of the atoms that are in a chemical bond. So what does that look like? If we have a bond between A and B, homolytic cleavage basically splits up those two electrons in that bond between A and B. Okay, and we can do that using these half arrows. This is how the mechanism would be drawn, at least. So that half arrow is called a fishhook arrow because it looks like a fishhook. And fishhook arrows are only used when we are kind of distributing or moving around a single electron. So they're used only for radicals. And since we have two electrons moving around, we have to have two of those fishhook arrows to show that they are going to A and B. Now, for unsymmetrical cleavage, this is called heterolytic cleavage, meaning different splitting of the electrons. And so if we have a chemical bond between A and B, we form A and B, and the lone pairs the two electrons went to B, and A lost out on them. That's why it has a positive charge, B has a negative charge. That arrow is just a normal mechanistic arrow, and that means we are using this to show the flow of electrons, two specifically, and this is just this is the most common one we'll see. We'll only see the radicals in very few reactions. So we can do the reaction in the opposite direction, so bringing those two electrons together forms A and B in that radical product, and then B can attack A to form a B compound, okay? So just to show you the flow of electrons in both directions. So let's take a look at radicals, carbocations, and carbanions. This is just going to be a generic kind of mechanistic pathways. One of them showing you the homolytic, heterolytic, and another heterolytic cleavage. So we have the two fishhook arrows here. That forms two radicals. That is a radical carbon, and that carbon is therefore an electrophile. It is electrophilic because it's electron deficient. That radical doesn't have an octet, and that is a homolysis cleavage, homolytic cleavage. Now this one, we have a normal an arrow showing the flow of two electrons coming away from that carbon, giving it a positive charge, and the two electrons going to Z. This makes that carbon right here an electrophile because it's electron deficient, it doesn't have all the octet, and it is specifically called a carbocation. Drawing the same compound, another type of heterolytic cleavage would be the electrons going away from Z. So the two electrons go on the carbon. That makes it a nucleophile because it's now electron rich and negatively charged, and it is called a carbanion. Anion meaning negative, cation and carbocation meaning positive. Okay? What do you think it is? It's time for practice. This stuff is really easy. I think you should try and go through it as quickly as possible. Don't worry about understanding every little bit of information because we're going to see it in chapter 7 like a lot. Okay, so just go through the material, get the gist of it, and then move on, and then come back if you need to. So these 3 compounds right here, what we want to do is, considering the electronegativity of the atoms in each of these compounds, we want to see what the products would be of heterolytic cleavage. Pause it and try it on your own and see what you get. Okay. What we also want to do, is classify intermediate compounds as carbocations, C+, or carbanions, C-. Okay. So let's take a look at the functional groups. Those are where all the reactivity happens, right? So we have an OH in this one, a Br in this one, and a lithium in this one. Everything else is just CHs, so those aren't likely to cleave. We can cleave it maybe that way or that way. So which one is more likely? It's more likely the electrons will go to the more electronegative atom, and so we would have the electrons going to the oxygen, making hydroxide and this C+, carbocation. And then we also have the C+ and Br-, and then the last one is going to be C- and lithium+. The reason why is because lithium is less electronegative than carbon, so the electrons go to the carbon, whereas bromine and oxygen are more electronegative than carbon, so they steal the electrons in heterolytic cleavage. Okay, so we got a carbocation, and a carbanion. Remember, carbocations are electrophiles and carbanions are nucleophiles. Have fun with it. That's it.